A quick show of hands, who is deploying machine learning models today? Okay, who is using TF Serving for that? Okay, who's using Flask? Okay, I'm curious about the difference then. Okay, I hope this is interesting for you. I want to show you how easy it is to deploy machine learning models, because the bad news is that most machine learning models won't get deployed. And there are a million reasons for that. And one of the key reasons is that a lot of people think that machine learning deployments, the deployment of the models is tedious, it's cumbersome. But I want to show you in the next 25 minutes that it's not the case. That's actually pretty easy and straightforward. Hi, my name is Hannes, and I'm the head of engineering at a company called Caravel, where we focus on conversational machine learning models. And in this small company, we continuously deploy machine learning models. So I have to automate most of this stuff, and I have to focus on easy deployment so that we can get this out with a small team. So what I want to show you in the next 20 minutes is sort of like how we do this and how we set up our deployment environments so that the models get out to the people who use them. So let's face it. You do all the hard work, you train all the machine learning models, but then you want to get the models out so that everybody else can use them. And the deployment of the machine learning models is what is between your hard work and the greater world. So I want to show you how easy you can do this, but a lot of data scientists ask the question, why do I really need to worry about machine learning deployments? Well, so we have these two fields. We have data science and machine learning on one side, and then we have DevOps on the other side. And there's currently a new discipline emerging, which is called machine learning infrastructure. But while this is sort of emerging and job descriptions are being created and formed, I think it's up to the data scientists to push out their models. The DevOps folks are really good at scaling models, at scaling microservices, at providing network access to the services, but they're not the experts of the TensorFlow ecosystem, or they're not familiar with the different standards on how to serialize models. So it comes down to the data scientists to push for the deployments. And what I want to show you in this presentation here is how you can deploy these models, and then you can either take it up to the DevOps folks in your company or your organization to show them how that can be deployed, or you can deploy them yourselves in the various environments you're using. But before we get into the details of how to use TensorFlow Serving, I want to show you an inefficient way of deploying machine learning models. This is a very simple setup of a Flask API. In this moment, we create an endpoint called classify. We take some form data. In this moment, we're having a form field called review, and we're pre-processing that through some function. Don't worry about this for right now. But then we do the model prediction on it. We use a Keras model here. We call the predict method on it. And whatever we get back from that method, we JSON-fy it and then send it back as a response to this HTTP request. A lot of people do that. A lot of blogs point out that this is a way to do it. But I think this is a highly inefficient way of doing this. And here's the reason why. Everything you do in this moment is highly inconsistent. You can create another model where your API standards or the API structure is completely different. Your payloads might be completely different. And so when you bring in new people to the team, they see one model and they see one pattern, and they see another model and a completely different pattern. Nothing is really standardized in that moment. If you use like a Flask setup, then it's up to you to define how you manage different versions of the model. And again, you run into these issues of different setups for different models, so it's highly inconsistent. And then you're using your precious hardware highly inefficient. What you want to do at the end of the day is you want to use mini-batching. And I will get to that later, what that means and how you can use this. And again, it's highly inefficient for large models. So these days, we're all talk about transformers. We talk about BERT, XLNet, and models in the gigabyte range. And in that moment, it's really inefficient to just load it in a Flask environment, and then maybe your web server like Unicorn spins up multiple environments, and everything gets replicated, and your memory explodes in that moment. So here's the rescue to this madness. If this would be my Flask setup. It works, but over time it gets really difficult to maintain. So the rescue to that is TensorFlow Serving. TensorFlow Serving is part of the TensorFlow extended ecosystem. As you know, in the TensorFlow ecosystem, there are a bunch of other tools around the actual model framework, which you can use to validate data, you validate models, you analyze the models, et cetera, et cetera. One of the tools is TensorFlow Serving. It has been battle tested at Google for many years, and I think it was open source like around 2 years ago. And it's highly scalable. And it allows you to deploy models easily for up to 2 gigabytes. And the reason why we're getting to this 2 gigabyte limit is just that the protobuf file format, which is used internally, has a 32-bit limit. But there are ways around it. So let me show you how you can quickly deploy machine learning models. But before we get to that point, you have to export your model. So let's assume you have trained your model, you've done all the validation, you're ready, you're good to go, you just want to get this out. So here's the 5-minute deployment. You export your Keras model. In this moment, it doesn't need to be a Keras model, it can be like a TensorFlow estimator, or it can be a graph. But basically what you do is, in the TensorFlow 2.0 world, you call a function called tf saved model. And then this will export your model into a very predefined data structure. So basically, your model gets converted into a protobuf file. And then you're going to see this folder structure and file structure. So your export will be timestamped. And the timestamp will be the epoch of that moment when you exported it. You're going to have a folder with assets, which could be your dictionaries, if you have like hash tables, or you have like a lookup of vocabulary. You have your actual protobuf file, which is defining your network. And then you have a variable folder, which is containing all the variable information of the different weights and things like that. So every time you export a model, you get a new folder. The timestamp is changing every time. So once you do that, in the remaining 4 minutes of your TensorFlow Serving setup, you pull your Docker, you pull the Docker image, and you basically start up the Docker run command with a bunch of parameters. First of all, you expose 2 ports. We get to that in a second, which services they're representing. You mount your directory where you exported your folder to, or your model to. You tell TensorFlow Serving which model it's supposed to load. In this case, the model is called my model. And then you just run the container called TensorFlow Serving. In case you want to do the inferences on a GPU, the only thing what you have to do is you swap out the container image name. All right, with that, you're going to see a bunch of output. This is an example output, what we run at Caravel. We run a bunch of like embeddings and language models. So in this case, it's a highly big, it's a highly trained model, and it's really big. And so it takes a long time to load it, and I think it's somewhere 18 seconds or something. But what you want to look out for are these red lines there. They basically tell you, hey, everything worked successfully, and you have 2 endpoints. We haven't programmed a single line of code, and you have 2 fully functioning APIs ready for inferences right there, 5 minutes. So in this moment, we sort of like had to link the machine, the models to the Docker container. We did this through mounting folders on the host machine. Sometimes and often you don't want to do this. You want to put them somewhere in the cloud, and you have like a GCP bucket or your S3 bucket. So you can easily load this out of the box. So in this case, the only thing what you have to change is your startup command of TensorFlow Serving. So in this case, you don't tell it, you don't mount the path. You just point towards the S3 bucket in this moment. You have to provide the credentials either inside of the container, or you load them as an additional Docker run command, and you're good to go. Again, you haven't programmed a single line of code. Works out of the box. Sometimes you want to load different models at the same time through the same instance. And the way you can do this is you define a model configuration file, and this is basically the file I'm showing you on this slide. You can define the different models with a base path. That's where the path where you can find all the different versions for the different models. And then you pass this additional configuration file to your TensorFlow Serving command, and you're good to go. The only one thing I want to highlight here is I would not use this in production, because if you run multiple models within the same container, maybe one model is more often used than the other one, and you want to scale them at different rates. So in this moment, it might make more sense to sort of like separate them by containers, and then you can scale them differently. Sometimes it's really useful to specify specific versions of your model. So remember, we exported the model at the beginning, and so you get the timestamps. Well, you can specify these timestamps in your configuration file, and you can tell TensorFlow Serving which models to load and which ones to serve at the time. So the standard behavior of TensorFlow Serving is that it will always serve you the latest model. So if you put a new model in that S3 bucket or GCP bucket, the server will automatically detect it and swap out the models. So again, you don't have to restart the service. You don't have to program a new line of code. You don't have to deploy the container again. Everything happens under the hood automatically. And sometimes you just want to serve two versions at the same time. And you can do this through the configuration here I'm showing you on this slide. And then sometimes you don't want to remember the version numbers. You just want to give it labels. And you can define, for example, a stable model or a testing model, and under the hood in your configuration file, you can swap out the version numbers, but your clients or the people using your inference servers just point at the keys or at the labels, and then you can swap out the versions under the hood, so everything stays the same. Again, you just change your configuration file, load it into your container, and you're good to go. So now with everything being set up, let's talk about how you can actually infer your models. And you have two options there. As we saw at the beginning when the server came up, you have two ports. You have 8500 and you have 8501. The first port is for the RPC protocol, and the second port is for a standard called REST. And here I'm going to show you a couple examples how you can infer on the REST side. So the REST protocol is pretty common. You basically have you have URLs, you make GET or POST requests, or the standard HTTP request, you submit some data, and then you get a response back. In this case, you submit your data to a very predefined URL structure, which is your host machine, your port you define, in this case will be 8501, and you give it the model name. In our case, it's like my model. If you want to specify a particular version, you see how you can do this. You just append it to the URL, and you're good to go. Nothing crazy. Once we have this, we can write a few lines of code, but this is pretty standard code. This is like the standard Python implementation with a requests package. So we define the path here. We create the inference data, which is basically, in this case, I have a little review model where I want to figure out like what's the sentiment of this text, and we pass a dictionary with a key called instances and a list of the different samples to the model server. In this case, I just make one request at a time, and then the response contains the score for each label in this case. So that's going to be then returned from the API. If you want to use the RPC protocol, the setup is a little bit more involved, and it's a little bit more code than what I would like to squeeze on one slide. So I won't show you the code for that, but the TensorFlow Serving documentation is really good, and you can pick up a lot of examples. But what I want to stress is sort of the workflow. So in this case, you would convert your samples into a protobuf format. And in this case, you define your data structures of the input field. So you basically say, this input is a string, this input is a float, et cetera, et cetera. And then you convert them into base 64. And after you created like a RPC stub, you have all these RPC methods, and then you can infer the data from the RPC service. And often the question I get is like, hey, what should I use? Should I use REST or RPC? And my standard answer to that question is like, if you want to go quickly, get something off the ground, use REST. It's easy to debug. You can use curl, you can use a browser. You're good to go in a couple minutes. But if you want the efficient way, I would recommend the RPC implementation, because that format was developed by Google, and it's used to reduce the network traffic, because you basically limit your your payloads, and it also becomes highly redundant or sort of secure in terms of the transmission. And the wonderful thing in terms of like model inferences is the inference is more efficient and faster. So if you submit it on the REST side, the server has to figure out what's the data structure, because under the hood, what it's actually doing is it's converting all your data samples into TF example records, and then it's inferring them under the hood. So if you submit them through JSON, basically the REST standard, then the server has to figure out, is it a string or is it an integer, things like this, and this is going to take time. So for example, in the case of MNIST, we have 768 fields in that list. Every time the server has to figure out, like, is it a string or is it a float? So in this case, if you use RPC, it's much quicker. A lot of people ask about A/B testing of models. And while TensorFlow Serving is not supporting this on the server side, very easily you can implement a client-side A/B testing. Remember earlier I showed you how you can define the different model inference URLs? Well, you can just swap out the version numbers. And here's a little function. Feel free to use that. We just define the path here, which then gives us the URL. And then with another little line of code, we can swap out the version number based on the percentage we define and the threshold. And if you pass in a non-value to your version, TensorFlow Serving automatically defaults to the default model. And if you specify a version number, then it will use that for 10% of the cases here. Sometimes it's really helpful on the client side to know some of the meta information of the models. And this is often being used in some information of like, hey, which model am I inferring here? What's the version number? What are the inputs? Can you tell me a little bit more information about the model itself? And TensorFlow Serving can provide you these information out of the box. So we have a little function here which is inferring very similar to what we have seen before. But instead of making a post request, we make a get request to this very similar API, and we append /metadata to the URL structure, and you're good to go. And what you see from there is a very lengthy data structure which tells you all the information about the models. And what it's actually showing is something called the model signature. It tells you all the inputs, the data formats, the names, and the outputs, and again, you get the names and the data structures. And you can use that in various forms and ways, and often it's like really good to, especially when you have telemetry systems, and you want to send some feedback from your client to another system, you want to know which model just inferred and gave you the prediction. So a lot of people say, I can do this with Flask, maybe not the last one, or but the next thing I'm going to show you, you can definitely not do with Flask, or you have to code a lot. So here's something which you get out of the box with TensorFlow Serving, which is an amazing feature, and I think it's highly underrated, and it's hard to find in documentation. You can do something called mini batching, which is a wonderful thing with TensorFlow Serving. So in the initial case of Flask, we saw that we made an HTTP request, you made the model prediction, and then it sent the response back. But in this basically request response loop, you basically locked up your hardware for that one prediction. Well, we use CPUs and GPUs efficiently so we can bundle together a bunch of samples, infer them at the same time, and then send out the results to the different clients again. And that way we can use our precious hardware more efficient. So let me show you how easy it is to do that with TensorFlow Serving. But in this case, you basically get a bunch of requests. Instead of inferring them one by one, you either wait for a limited amount of time, or once your batch is full, you infer. And then you're good to go, and you send it back to the clients. The configuration is super simple. You define a text file with the information I show you here on the slide. You define your batch size. You define your timeout, how long do you want to wait. And you have a couple other options of like batch threats and batch queues, how many queues you want to use and things like this. But the bare minimum definition is something what you see on this slide. And then, again, you don't have to code. You just load that additional configuration file. You mount the directory where you can find that file. You tell TensorFlow Serving that you want to enable batching, and then you pass in the parameter file. and you're good to go. One thing I want to highlight here is like if you have different business cases, so for example, if you want to do batch processes, you want to have a long timeout and you want to maximize your batches. But if you have real-time applications, you want to reduce your timeout and you want to be really tight on how many milliseconds or microseconds you want to provide or you want to wait. So for most applications, you actually want to be somewhere in between. So that requires some trial and error to see how big is your batch size. You can watch this on your GPU with the memory usage, and then you can see what the latency is on your entire application. So I would advise you to just try and error with the parameters there. There are a couple more optimizations I want to point out. And again, it's fairly easy. You just have the additional parameters you pass into your Docker run command. And you have a couple parameters here. And I want to point out the first one specifically. Initially, I showed you the slide of like how to load remote models. So if you have a bunch of versions in that remote bucket, by default, TensorFlow Serving goes to the bucket every 2 seconds and checks is there a new model available or not. It does that polling. So over time, that can occur a lot of like charges because you basically do a list request and you submit a bunch of data back with all the model information. So in this case, I would change the polling time. It's going to save you some money. And then you can, if you don't want to use all the cores for TensorFlow, you have a couple of options there. But yeah, feel free to play around with the configurations. And again, you just pass them in as additional arguments. And then as the last optimization I want to point out, with machine learning models becoming bigger and bigger, these days we talk about quantization, we talk about pruning. You can use TensorRT together with TensorFlow Serving. And you can use the NVIDIA tool by converting your model with the saved model CLI tool, which is a wonderful tool also to inspect your machine learning models in case somebody else developed the model, there's no documentation, you can inspect the model and it shows you the entire signature, what I showed you earlier with the metadata. You can also see this in your command line with the saved CLI, model CLI tool. You convert this model and then you start TensorFlow Serving with a runtime argument for NVIDIA. You point the model towards the optimized model and you have to use their GPU container because it's NVIDIA, so they want to use their GPUs for that. With that, a quick shout out to the folks in the room who might have some PyTorch models. You can use Onyx. Onyx is an exchange format for machine learning models. And they have their own runtime engine, which you can use in various environments, like browsers, edge devices, and servers as well. Quick note on what's the sort of the future of the model deployments. One thing you can use today is TensorFlow Transform. Anybody use TensorFlow TF Transform? Cool. It's a wonderful package. I'm highly, I drank the Kool-Aid on the TF Transform, so I have to be careful. Because the wonderful thing is, especially with TensorFlow Serving, you can convert your pre-processing steps as a graph, and you can connect them with your model itself. So what I do these days, I deploy them as a bundle. That avoids sort of the misalignment of my pre-processing functions and my inference models, my model definitions. And in that case, I can offload the entire pre-processing to the model server. That's usually a really performant machine, and my clients don't have to worry about tokenization and like converting to word vectors and things like this. The wonderful thing about the TensorFlow ecosystem is that the protobuf files or the folder structure I showed you earlier of the exporter models, you can use them today to deploy your models to edge devices and the browsers, for example. The only thing is what you have to do is you have to convert these exported models to something what JavaScript can understand, but everything is based on this one exported file, what I showed you earlier. There's a wonderful development happening around kubeflow pipelines. So if you build entire machine learning pipelines and you want to do some evolved A/B testing or you want to do some model routing, I highly recommend kubeflow. There's a wonderful package as part of the kubeflow package Kubeflow program. It's called Istio. Istio is normally used for like routing web traffic between containers. But you can use it in the setup for models as well. So you can phase models in and out. You can do some A/B testing. It's a wonderful setup. So I highly recommend that. And then what's going to have a big change on the way we probably deploy machine learning models in the future is federated learning. So instead of the clients submit the data back to the server, we make the inferences on the client side and then sort of build these mesh networks and put them together. So I'm looking forward to see a couple changes there in the future. I want to just a quick shout out. My friend Catherine and I were working on a compilation of like teaching data scientists of all the things you need to do before you train and after you train. And if you want to learn more details about how to deploy machine learning models, I highly recommend this publication. We're trying to get an early release out for TensorFlow World. And with that, thank you, and I'm looking forward to your questions.